We're going to work through an example of output analysis where we look at a data set and calculate out the mean, standard deviation, confidence intervals, and then look at the desired relative precision and desired absolute precision to determine the number of simulation runs that we need. The example is that we're running a combat simulation to evaluate the use of a new weapon platform for its lethality. We ran our simulation 10 times, and we're quantifying lethality by the number of enemy casualties. The number of casualties for the 10 runs are 7, 5, 9, 6, 8, 8, 9, 6, 7, 7. So what we're going to do is we are going to load up Excel, load up our T-table, and work through this. So let's start by entering those data points. So we have 7, 5, 9, 6, 8, 8, 9, 6, 7, 7. Just to check, that is 10 data points. So let's start by calculating out the mean. So mean, we're going to use the average function in Excel, highlight the cells, and we get that the average is 7.2. Now, if we want the standard deviation, we can similarly just use the stdev function, highlight the cells, and we get a standard deviation of 1.31. Now, if we want to do the confidence interval, we need the t-value. So over on the right-hand side, you can see the t-table from the combat modeling notes. We have n equals 10, and suppose we want to do a 95% confidence interval. That means that the tails are going to be 0.05. There's two tails, so we're going to look at the column for 0.025. So we're going to look at this column right here. We're looking at n equals 10, so we're going to look at n minus 1 on this table. And we're going to use a value of 2.262. In that case, we can now calculate out the confidence interval. So the confidence interval is an interval. The negative or the lower bound is going to be the mean minus your t-value times the square root of your standard deviation squared divided by n, which is your number of runs, which in this case is 10. So we get that the bottom end is 6.25. The positive confidence interval is going to be the exact same equation with a plus sign there, and we get it being 8.141746. Now, suppose we wanted a desired absolute precision of 0.5. What this means is that our confidence intervals would go from 6.7 to 7.7. So we're trying to shrink in our confidence intervals. Right now we have 10 runs. How many runs will we need? So we can use the equation where n equals your standard deviation times your t-value divided by your desired absolute precision. And it's that value squared. So we're going to need 35.47. We round up, so it means we need 36 runs. However, our t-value is going to change if we have 36 runs. So we can look up the t-value in here in this table for 36 runs. It's going to be it'd be a value of 35, so it'd be halfway between 30 and 40. So it would be about at 2.031 for our t-value. We can then recalculate out the number for n. We can just use the same equation, copy and paste it, but switch the t-value to being our new t-value of 2.031, and tells us we need 29 runs. So we can repeat this process again. T equals 29, it's right here, 2.048. And we can reuse our equation. And our new t-value, 2.048. This is telling us we need 30 runs. 30. So if we look at that, it's going to be 2.045 for our t-value. And according to our desired absolute precision equation, is going to be this says 29. So you can see if we, in this case, we would be alternating between this equation, and we would, And so we just go for the higher number. If we do 30 runs, we'll be able to achieve a desired absolute precision of 0.5 KIA. So that's great. Now, suppose we wanted a desired relative precision of, let's go for 5%, so 0.05. So now we use a slightly different equation where it's equal to the standard deviation times our t-value divided by our desired relative precision times our mean. And all of that's going to be squared and tells us we need 69 runs. So we would do the same thing again. For 69 runs, we would need we'd have a t-value of around 2.00, going right down here. At 120, it's at 1.98, so at 69, it'd probably be pretty close to 2.00 still, in which case our new value of n is going to be, move our t-value to down there, 54. So t n equals 54. Go back to our table right here, and it'll be about 2.005. And so that's just interpolating between 40 and 60 based off a value of 54. And so our new value of n is going to be 54. So we converged. We need 54 runs to get a desired relative precision of 5%.